So hi, so this is the second phase of microstrip patch antenna. So as so we were like we want to design a 10 gigahertz antenna. So in the first phase we designed a 28 gigahertz microstrip antenna. So in this phase we are going to design a 10 gigahertz microstrip antenna. So you have like two antennas which are used for different applications. Okay. So here as in the first place we have seen that these are the this is the design of microstrip antenna where you can see that where you can see that the this is the ground and there is a substrate, and these are the width and length of the substrate, and there is a patch, and this is the feed line, and this red one, this is the port where you are giving the input voltage, and this thing is gap. It's called as the inset, or it is also called as the gap, which is important in microstrip patch antennas. So this is the general design. So we are following the same equations and same designs and everything. So this is the equations. This height of the substrate is there, patch width, patch length, and everything. But we are doing everything for um, 10 gigahertz resonation frequency. So actually, whenever you're designing an antenna, you have three things which you have to keep in mind. First one is the resonant frequency, and the second one is the substrate, the dielectric constant of the substrate, and the height of the substrate. Okay, so we're designing the similar thing for 10 gigahertz. Wherever the frequency, you can see resonant frequency, there you have to substitute 10 gigahertz, and the height will be, I think, same. I think it is like when you think height, you have the height of, just a minute. Yeah, 1.6. Yeah, we have the height of 1.6 millimeter, and we're using FR4 epoxy, which has an dielectric constant of 4.4, 4.4 epsilon. Okay, so these are the equations, and we are doing it based on these equations to get 10 gigahertz frequency, right? So let's go to the software. So this is the software. Okay, so whenever you're designing antenna, you have like three main steps are there. First one is to design the design itself. Design as in to design the ground, the substrate. You have to give the dimension. You have to place the antenna patch, substrate, and ground in the proper place. That is called the physical design. So we first do the physical design. After that, you have to give this. We have discussed already in the first phase. After the design, you have to give the boundary conditions, and then you have to give excitation, and then you have to give the frequency sweep, which is the analysis. After these four like steps, you can get the output. Okay, so first let's go with the ground. So first we are you can see that all the whatever ground or whatever part I'm designing, you can see everything here. And here you can this is called as the project manager. Here you can see everything, boundary, what are the boundaries you have given, excitation or analysis or results or everything, you can get it here. Okay, so first let's go with the model. So here you can see what are the models I've used. Yeah, you'll get everything. Okay, so this is the ground. So when you click on the ground, so ground will be, yeah, you can see that the ground is being highlighted, right? So in the bottom part, in the lowest part of the antenna, you have the ground. So if you want to see what are the dimensions I've used for ground, just have to double click this create rectangle. Here you can see there is x size, y size, and there is also position. What are the exact position where I have places ground. Okay, everything is visible here. Whatever dimensions I've used in this model, everything will be visible in the software. You don't have to worry about everything. You can get all the dimensions here. Okay, so this is the ground. So after the ground, above that there comes substrate. So substrate has a height. So ground, we were designing ground, it is actually like a sheet, right? It doesn't have a height. But substrate, it has a height. So it should be a solid. So you can take a solid from here. That's all I have explained in the first phase, and just you have to draw it, because I'm not making any changes in this model, because I cannot make, because I have a valid solution. So if I make any changes, the solution may be disrupted. So I'm not making any changes. So if you click it, and when you click and drag, you will get the solid. So this is a substrate. You just double click the substrate, you can see this height is 1.6 millimeter, and these are the x and y sizes and position, everything. It is all given. Now you have to select the material. So here you can see the material. You can edit material if you want. You can edit the material. There are different kinds of material here. I'm selecting the FR for epoxy, which has a relative permittivity of 4.4 epsilon. Right. I'm selecting that as the dielectric constant, and this is a substrate. So then you get your substrate, and after your substrate, this is your substrate, and above the substrate you want the patch. So for the patch, yeah, this is the patch. You can see that I have united many things, I've subtracted many things. So first what I'm doing is I will make a patches of dimension, yeah, xy size here, I can position, everything is there. So first I will make a patch. After making patch, I will create two more rectangles, which is a slot. You can see that there is a cut here, or slot. So to cut this, or to make the slot, after creating the big patch, I will create two more small rectangles. So this is known as slot 1, slot 2. You can see slot 1's x size, y size is there, position, everything is there. After doing that, after creating all these three rectangles, you can just click it, click, then control click. See, you can just select everything, and you can see that there are, now I cannot do it, but there will be many unite, subtract, there is intersect and everything. So what you can do is you can actually subtract these slots from the patch, and you'll get this lot. So there will be this is actually a big rectangle, and you have two small rectangles, but you're subtracting the rectangles from this, so you will get a slot kind of thing. So this is like a hole kind of thing in the patch, right? And after that, you have to go for the feed line. Feed line is this big, this feed line which you can see. So here also I have created feed line separately. This is the xy size and position and everything. Then I have united this patch and the feed line. So first what I have done is I have created this big rectangle, and then I have created this small rectangle, and I have united them. Okay, so I will get this sort of big rectangle and this. Okay, it will be like one, like this. And after that I have subtracted these two small rectangles. Okay, so this is how a patch is formed. So after the patch, you have to give your port. So port is in the YZ direction. So all of these design which I have shown in these are on the XY plane, but this port, it is in the YZ direction. So port also, you can see there is, yeah, so this is where you can see the dimensions of the port, x-axis, y-z, and position, everything. You can see the port, right? So now we have completed the design. Sorry, we have not completed. There is one important thing. After making the antenna, you have to make sure you put a box around the antenna, which is called as a radiation box. So if you don't put this box, you won't get any radiation pattern from the antenna. So it is very important to put this box around the antenna. Okay, so this is the radiation box. You can find the dimensions. There is no particular dimension for this. The thumb rule is that the antenna should be inside this box, and it should be, it's a big box, it should like surround the antenna. So there is no specific um, dimension for this box. You can put anything you want. Okay, it should be, make sure that the antenna is inside this box. So we have designed everything. So we have the box, we have the ground, substrate, patch, feed, port, everything. After this, so our design step is completed. So after the second thing we have to do is give boundaries. So you can see that, so there are like two boundaries. First one is radiation boundary, which is the box. So here, just right click, you can see the boundary. This is the radiation boundary. right? So it means that we are saying, telling the software that the box, it is covered in air, so you can see the material is air. We cannot take any other material, we cannot take vacuum and all, because in vacuum you can't see the radiation pattern. So you have to take air as the material inside the radiation box, and you can give the boundary as radiation. And second one, you have perfect E. Perfect E is like conducting. Perfect E is like perfect conduction. You can see, if I zoom it, you can see that ground, yeah, and the patch, both of them are perfectly conducting. Perfectly conducting means it is like antenna patch has to be copper or aluminum or something which conduct the input, whatever signal you're giving, it has to conduct it or radiate it. It should be conducting, right? So you can just right click, assign boundary. There is something called as perfect E. So you can put perfect E. So there are only two boundary. First one is radiation, second one is perfect E. Radiation is for the radiation box and perfect E is for the ground and the patch. Clear? Now our boundaries are also over. And then last one is excitation. So when it comes to excitation, this is where I told you there is something called a sport. We make something called a sport. This is where you are actually giving the. So we were talking about. Just a minute. Yeah, so there are some technical problems. We were talking about excitation, right? So yeah, let me do with excitation. Okay, so when it comes to excitation, yeah, this is the port. Just a minute. Yeah, so this is the port, right? This is where you can see the excitation. So we have done with our two steps, which is designing as well as we have done with designing as well as boundary conditions. Now we have to give excitation. So in this excitation, so this is we are giving it in the port. So just you have to click the port, and when you right click, you can see there is assign excitation, and you can just assign lumped port. You can see that there will be excitation here. So we have done so this is how excitation is actually like an input signal, right? For radiation or for getting some output, you need to have some input signal. So excitation is that. Okay, so this is where you're giving your input signal, and you can see that this input signal is connecting, it is actually connecting ground as well as this feed line. So the input signal, you can see that it is like a this is like a transmission line kind of thing, right? The signal is transmitted to the patch, right? So you have given, so our three of our, sorry, so three of the uh, steps is over. We have designed, we have given the boundaries, or we have given the excitation. Next one is analysis. In analysis, we have to give sweep. Sweep is nothing like you have give like 5 to 15 gigahertz. So what is sweep is that now we are designing it for 10 gigahertz, right? So sweep should be such that our resonating frequency should be in between them. Like you can take, if it is 10 gigahertz, you can take the sweep as 9 to 11 also. That is also fine. But I've taken a little bit more so you can understand it properly. So I've taken it as 15, 5 to 15 gigahertz with step size 0.1. So if you display it, you can see that this 5, 5.1, 5.2, this is how the frequency is being generated. So what is sweep, or what the software does with the sweep is that you have the model. Now you are testing the model by giving it frequencies. Okay, you give 5 gigahertz, then you check whether the antenna is resonating. You give 5.1, then you check 5.2, then you check, and then you check till 15 gigahertz. You will see that at one point or at one particular frequency, our antenna will start resonating. So to find that frequency, we are testing the antenna with different frequencies. That is the purpose of giving sweep. Okay, so after sweep, you have finished everything. Now you have to validate your model. So you have to check whether everything you're getting it as green tick marks, right? If you get any red color cross mark, it means that your model is not correct. It cannot be validated. So if you get everything like green tick marks, it means that your model is correct and it is validated, right? So now you can go and you can analyze or simulate everything. So if you click this, the model will get simulated. Right, so I have already simulated the model and I have got the results. So I'll show you the result. So in the result you can see that, yeah, so this is our return loss, and you can see that our antenna is resonating at 9.9 gigahertz, which is very good because 10 gigahertz is of frequency, right? So 9.9 gigahertz is very good. So it is resonating at nearly 10 or 9.9 gigahertz, where you can see that the return loss is at the minimum. Okay, similarly you have a VSWR, which is also at minimum. In at 9.9 gigahertz, we can see that VSWR is also minimum at this particular point. And again you have radiation pattern. So this is the radiation pattern, and this is the 3D radiation pattern. So you can check the 3D radiation pattern. Yeah, so this is a radiation pattern. So you can see that at the top portion, the red portion means there you are getting the maximum radiation, and the radiation is getting less when it comes to the uh, bottom portion. The radiation is decreasing, and here you can see that there is some blue color line. Blue color, it means that the radiation is very less or nil here. So at the top part you are getting the maximum radiation. Okay, so this is how you design a, I'll just fit it all. Yeah, so this is how you design a microstrip antenna